All right, so today we'll be covering workshop number 3, using the scientific method and engineering design process, writing a problem statement and goal to organize data. So I'm going to talk a little bit about the agenda. So today we're going to look at the overview of the scientific method and engineering design process and components of the scientific method. So how to write each component and examples of each component. And we'll also do the same thing for the engineering design process and some examples. And finally, we'll look at collecting and organizing data and/or test results.
Projects that we cover in GSDSEF, and that's the engineering design process and the scientific method. So if you're planning on doing a scientific process, the first two steps you should do is try to gain some knowledge about your topic and then figure out an hypothesis you have for your experiment and predict what would happen if some variable is changed in your experiment and collect data to answer that question. If you're doing an engineering or computer science design, then your project will be a little different because you're constructing something rather than testing the effect of something. So that's mainly trying to find the solution to a problem or trying to improve an existing product to have a better application. And your question for those types of projects can be, can I build or create a better application for some existing topic? So for both of these projects, we'll have a slightly different approach. So for the scientific method, this is an in-depth explanation of the entire process you can go through, from asking a question to background research, and then the hypothesis experiment and revising based on the results you have to maybe construct a new hypothesis, and different experiments you can go through over and over again to find which design works the best for the effect you're trying to have. For the engineering method, you define the problem, do background research, and then you have to try to find specific requirements for the goal you're trying to achieve. So that can involve what materials you want to use, what different solutions you want to try out, building the prototype, building the actual product, or changing the design and prototype if it doesn't work and meet the requirements you want. For all of your experiments, whether you have a scientific or an engineering project, you should keep a raw notebook for all your data. So while you're doing your preliminary tests or you're doing your different trials, you can just jot down the results in a notebook. These are your handwritten notes, or when you're brainstorming what materials you want to use or any sketches you have for your prototype. And then you just keep all the stuff in the raw notebook that you can include when you're submitting it later on. And this just includes your notes, your materials list, sketches, data collection real time, any pictures or drawings you want to tape down, your prototypes, all of that. So just as you're brainstorming, your initial thoughts can all be put in your raw notebook. Then for your final presentation for GSDSEF, this is something you have to actually submit to the judges. And this is a more refined version of your raw notebook. So here is where you're going to contain like all of your different steps for your method, your background research, your procedure, your finalized results, and your refined tables and all of that. And then you can put this in either a binder or print it out. And some people put it in front of their posters as like a printed out section that's like bound together in some form. And they should all be easy to read and understandable. If the judges just go through your notebook, they should get a really good understanding of your entire project. And then if you want to include some of your raw notes here from your raw notebook, you can put them at the end. But your finalized notebook is actually required for your presentation for the judges to see and have like a revised, presented, good version of your research.
So on the GSDSEF website, we also have a sample science notebook. So I'm actually going to go ahead and open that now. So if we get to the gsdsef.org website, student resources, and we'll scroll down to section D. In big font, we have the GSDSEF sample student science fair notebook. It's a PDF, and this has everything you'll need in your science fair notebook. And at the top, there's also sort of a checklist you can go through to make sure your own notebook has everything you need. And we'll actually, in some of the slides ahead of this one, we'll also be referring to some of the pages. So if you want to come back to this later and just see the sample alongside what we were presenting, feel free to do that. So back to the slideshow now. The next part of your notebook besides your cover page should be the background research that you've done on this topic. So this should address some of the basic questions in your project. And this would be, what is the problem and its history? Why is it important? What have others done to test or address it? And why is your method the best way to investigate it? And there are a minimum number of citations that you have to follow for different divisions like senior and junior. For junior, it's 5, and for senior, it's 10. But you definitely want to go beyond these minimum number of citations to get the best background research possible. And if you're following the sample notebook, this should be page 2. Next is your statement of problem, which identifies the relationship that you're trying to test or investigate. And usually it just simply states how potentially changing one factor or variable could affect another variable. So if you're following along in the sample notebook, this should be page 3. And an example of this is what is the effect of blank on blank. So you can follow these questions to make your problem statement. The definition of a hypothesis for science projects is a proposed explanation or prediction of what you think will happen. So this would be based on your research and the problem you've identified specifically. And the most important thing about your experiment is that it's testable and replicable. So a great kind of hypothesis we recommend is the if-then kind. It should contain an independent and dependent variable, for example. So if temperatures are raised in orange juice, then ascorbic acid concentration levels will decrease.
So for your materials list in science projects, you're going to want to be very, very specific and also make sure to use the metric system. So here we can see that in this example that you can also find on the notebook, they specify the specific name of the company. So 2 packets of the name of the company, radish seeds. And then also when they use the plywood, they're giving the exact dimensions in centimeters, not inches. And then you also kind of want to follow the same steps when you're designing an experimental procedure. You want to be very specific with what you've done, and you only use metric units. An important thing with your experimental procedure is that it should be detailed enough for someone to repeat your experiment. Then when you're trying to think about your trials, you want to have enough data in order to make a strong conclusion. So these are just some examples here. So for instance, if you're working with like human subjects, you want to have at least 50 volunteers. If you're doing some other studies, you want to have 3 to 8 trials with 10 to 30 data points in each. Or if you're like working with plants, like in the example notebook, 30 plants per experimental group and at least 30 plants in the control group. Now, if you're in engineering projects or computer science projects, this is kind of some other steps you would follow. So first, you would be trying to define a need or express a goal for your project to solve. Then you want to establish your design criteria and constraints. Then you're going to be considering different designs to solve that problem. Then you're going to be building a prototype of your best design or your favorite design to test out. Then you're going to be testing that design and evaluating the prototype using your design criteria. Finally, you're going to be analyzing your test results, making changes and retesting that prototype. And then finally, you're going to be communicating the results.
The next step is that you do need to organize your data in tables. So there are a couple of strategies that you can do this. So your independent and dependent variable are either going to be the columns or rows in your charts. And you should write down all your data. And it may be a good practice to write it in like an Excel or Google Sheets table so that not only could you easily graph it, because those types of softwares have those basic graphing calculators in them, but you could also keep it with you at all times and access it from anywhere. And so graphing your data illustrates trends that you can't just figure out from a glance, which is going to be important because you will need to make correlations with your data when you're analyzing it. So here's one example of a way to visualize your data. This is a table. So you have the independent variable on the left, and the time is the independent variable. The dependent variable is in each subsequent column. and growth. So the growth in centimeters is the dependent variables. So you're going to have to label your table and trials with titles, and make sure to label your variables with units so that, for instance, you could label them like centimeters, days, or weeks. And although these look impressive, they may be difficult to understand at first glance. So the more organized your tables are, the easier they will be to graph, which is where you really draw your conclusions. You could also use a line graph. The line graph is usually used to show the change of information over a period of time. And you could, so typically you have these line graphs that are derived from a table, like we just saw in the previous slide. And you should note here that we make these workshops for a range of levels. So if you already know how to do this with, that's great, just bear with us. But if you don't, that's also to be expected. So don't worry about that either. So here's a simple table. To graph first, we need to look at the axes. The independent variable goes on the x-axis, while the dependent variable goes on the y-axis. To plot the first point, we need to take x from weeks, which is the independent variables, and then y from the height, the dependent variables. And essentially, you keep plotting like this. So you have 3 different data points, connect them with the line at the end. So the next 2 workshops, we will cover data and analysis in more depth, as well as to use some basic graphic software. And here's another option to visualize your data. These are bar graphs. So typically on bar graphs, you will see your independent variables lined up on the x-axis with their corresponding dependent variables shown on the y-axis. So here, each independent variable is the brand of car, and each of the corresponding dependent variable is the number of each car of each brand that was observed. So you'll essentially have the maximum, or I guess like the height of each bar, that will be the exact corresponding dependent variable. So Chevrolet reaches a height of 15 number of cars, Ford reaches 17, and Dodge reaches 10.
So now we're gonna stop the recording here, but just before that, we do have, like Ethan said, our next 2 workshops on data analysis in November. We have a basic and an advanced, depending on your skill level with data analysis, but feel free to attend both, and we'll be sending more information about that later.